Hello, everyone, and welcome back. In the previous lecture, we introduced the completeness axiom, which uniquely identifies the real numbers as the limits of Cauchy sequences of rational numbers. Now, we use the completeness axiom to show that bounded sets must have a least upper bound, and I left it as an exercise to you to show that there is a greatest lower bound. Now, these definitions naturally led us into the definition of the supremum and the infimum. Today, we're going to continue that discussion with supremums and infimums of sets. And in particular, what we will focus on, at least initially in this class, is monotone sequences, sequences that are either increasing or decreasing. So let's go ahead, let's get started. The first definition of the day is going to be exactly that. It's going to be these monotone sequences. So let's start it off with this definition. So we have the definition. We're going to say we call a sequence xn. We're going to call this thing increasing if each successive element is bigger than the previous one. So provided xn is less than or equal to xn plus 1 for all n greater than or equal to 1. And we write this symbolically as xn and then an up to the right arrow, right? So you can think of these xn's as sort of moving up the ladder in some sense. So similarly, a sequence xn is decreasing, so you can probably figure this out. So it's going to be decreasing, provided xn is greater than or equal to xn plus 1 for all n greater than or equal to 1. And we write this symbolically as xn and then a down to the right arrow. So again, we think of this sort of number line as proceeding to the right. That's why everything is sort of pushing to the right. The up or down tells us increasing or decreasing. Now, in either case, we call xn a monotone sequence. So if it's either increasing or decreasing, it is just referred to as monotone. And we can add a little bit more to this. And if those inequalities are strict, then we say that these things are strictly monotone or strictly increasing or strictly decreasing. So let's just round out this definition here with strictly. It's important that we separate these things out. I know it's a lot of writing, but we should have these things compartmentalized, right? So the original definition for increasing and decreasing is greater than or equal, right? We have equality possibilities here. So a constant sequence of all ones, that's technically a monotone sequence because it satisfies these inequality conditions. But if we say it has to be strictly greater than for all n and greater than or equal to 1, we write xn and the arrow is just pointing straight up now. So increasing straight up, and call xn strictly. So let's put this in red, strictly monotone increasing. So we're sort of combining all of these things together. The strictly, again, comes from the strict inequality. And of course, we're going to round this off. We're going to do the same thing for decreasing. So, and if xn is greater than xn plus 1, strict inequality, for all n and n, we write, so you can probably guess the symbolic representation here, xn with a straight down arrow here, and call xn, we call this thing strictly monotone decreasing. Okay, so that's a lot of definition to start off with, but this is important, right? We have to have the right nomenclature in order to speak about these things appropriately. So now that we have a definition of increasing and decreasing sequences, let's start with our first result of the lecture. So this theorem is going to say, if xn is an increasing sequence, then xn converges to the supremum of xn. So remember, we defined the supremum in the previous lecture. And similarly, if xn is a decreasing sequence, then xn is converging to the infimum of itself. Now, there's a major caveat that needs to be put in here, right? If you go back and look at the definition of the supremum, let's focus on that for a second. The supremum can either be whatever the least upper bound is, if your set is actually bounded, or it could be infinity. Now, think about what this is saying. First of all, if your set is actually bounded, so if the supremum is a finite number, this is saying that you have a convergent sequence, right? You're sort of increasing up and you have a wall that you hit, and whatever that wall is your limit. But if this thing is an unbounded sequence, say xn is equal to n, right? So all of the natural numbers, that's unbounded. We saw that the supremum of that thing is equal to infinity. So what this is telling you is that the sequence is diverging, right? So we have this symbolic representation of a sequence going to infinity. We say xn, right arrow, infinity. Now, this doesn't mean this, right? You could never write this in terms of convergence because infinity is not a number. So I want you to be very, very careful about what's being said here. Remember, the supremum can either be finite or infinite. And so when it's infinite, we understand this as diverging to infinity. Remember, we gave this definition in the second lecture. Okay, so that means that the proof of this is going to be broken into two different components. It's going to be broken into the fact when the supremum is infinite or when the supremum is finite. So let's talk about case one. We'll start with the supremum. The proof with the infimum is almost identical. I'm going to just do the supremum. So if your sequence is not bounded above, which is telling you that the supremum of this thing is equal to infinity, we see that for all m and r, there exists a capital N, a natural number, such that xn is greater than capital M. Right? So this comes from the fact that your supremum is infinite. This thing is unbounded. I can always find a number as big, or an element of the sequence is as big as I want. So I say, okay, here's a big number, say capital M. I can always find something beyond that. But then, if I look at all of the elements beyond capital N, this implies from the increasing property here, xn is greater than or equal to x capital N, which is greater than m, too. And so we see that xn is approaching infinity, which is just the supremum of xn in this case, by definition. Right? This is just from the definition of a sequence approaching infinity. It says if we define some cutoff point arbitrarily large, every element of the sequence beyond some point is above that cutoff point. This is just the proof. So let's look at the case when the supremum is finite. So now suppose the sequence is bounded above. And so we let L equal to the supremum of this sequence. So we're going to call that L because it's going to be our limit. And of course, this is the least upper bound coming from the results from the previous lecture. So we want to show, so sometimes it's important when we do proofs to write down exactly what it is that we need to show. So we want to show that xn converges to L as n goes to infinity. Well, we're going to do this by the definition of convergence. So that means we need an arbitrary number, epsilon, bigger than 0. So any epsilon that you can possibly find, I'm going to show that xn minus L is smaller than epsilon in absolute value. Okay, first of all, since L minus epsilon is less than L, right? I took a little bit off of the supremum. By definition, L minus epsilon cannot be an upper bound on xn. Now, why is that the case? Well, this just comes from the definition that the supremum is the least upper bound. And that says that if you take anything smaller than the least upper bound, it doesn't work, right? There's elements of the set that are above that thing. So that means that there exists some capital N such that you have L is greater than or equal to x capital N, right? That's just the definition of the supremum. It is an upper bound, but we found that x capital N so that it is an element of the sequence that is above this thing that we said cannot be an upper bound, L minus epsilon. So thus, for all n greater than or equal to capital N, we have, well, let's take a look at this. We've got L minus epsilon is less than x capital N, which by definition, this is an increasing sequence. So this thing is less than or equal to x sub n, which is less than or equal to L, just from the fact that this L is an upper bound on the set. And of course, this could be very trivially said to be smaller than L plus epsilon, right? If I add a little bit to L, it's going to be bigger than L. Now, here's the point. This gives me L minus epsilon is less than, actually, let's make this inequality strict, of course, because epsilon's positive, xn, which is less than L plus epsilon. So maybe we can just draw some arrows where all of that came from. I just extracted the important pieces out of that inequality. And then I can say L is less than, minus epsilon is less than xn minus L, which is less than epsilon, which is the same as saying xn minus L is less than epsilon. So since epsilon was arbitrary, so since epsilon greater than 0 was arbitrary, we have xn is approaching L as n goes to infinity, right? So that's just from the definition. Remember, the definition of convergence says that xn minus L in absolute value is less than epsilon when we look at the n's, the subscripts, n's large enough. And that's what n greater than or equal to capital N gives us. The other case, so the decreasing case, so let's just put this as a little note, is nearly identical. So we're going to omit that. And so omitted. Okay, so it's omitted. It's left as an exercise. If you want to sort of challenge yourself a little bit, try it out, try and prove that it should be almost identical to what we just did here. But we have an immediate corollary that comes from this thing. And this corollary says that if you have a monotone sequence, right? So a monotone sequence, this thing will converge if and only if, so it's a logically equivalent thing to say, it is bounded. So we're not going to prove this because it's an immediate consequence of the previous theorem. Why is that? Well, the sequence is monotone. If it's bounded, the supremum exists. Sorry, the supremum or infimum exists depending on if it's increasing or decreasing. And therefore, we just proved that it converges. Similarly, we've already proved that convergent sequences are themselves bounded. So these are the logical equivalencies that are coming into these statements. Okay, so let's move a little bit further into this and let's get more into the weeds. Let me define, or let me give you another definition here. So this definition might be a little bit of a head scratcher, might be a little bit of a brain bender, but let's take it sort of step by step and let's see what it says. So we're going to say let xn be any sequence of real numbers. Okay, so you give me any sequence, doesn't have to converge, doesn't have to do anything special, just give me a sequence. We're going to denote this set T sub n, which is all of the elements beyond n, right? So T1 is just the whole sequence. T2 is all of the elements of the sequence beyond x2. T3 is all of the elements of the sequence beyond x3, and so on and so forth. And we call this the, let's put this in red. Again, it's a definition, the nth tail. So T stands for tail in this case, of the sequence xn. Okay, so we're going to, so this is our definition here. Okay, so we introduced what we call the tail. So you give me a value of n, I cut off the sequence. I say, don't look at anything before that value of n, just look at everything after. So these themselves are sequences. They are collections of elements, right? They're not just a single real number. As I said, T2 is the entire sequence beyond x2. So x2, x3, x4, x5, all the way out. So these are themselves sequences. Now, let's put some notes up. As I said, T2 is looking at all the elements from x2 on. T3 is all the elements from x3 on. So you can see that you have this nesting here. So T1 is the original sequence. Well, that contains all of the elements from T2, which contains all of the elements from T3, right? Moving from one to another is just taking off one element from the sequence and looking beyond. And so you get this nice nesting property of all of these tails. Okay, so now what we'll do is we're going to define, we're going to call I sub n equal to the infimum of Tn. And we're going to call S sub n equal to the supremum of Tn. So I know that we're sort of going down the weeds a little bit, but you're going to say, okay, pick a value of n, look at the tails of this thing, and tell me what the infimum of the tail is and the supremum of the tail. So again, we have a note. You can see that in is less than or equal to Sn. This just comes from the fact that one is a lower bound and one is an upper bound. This holds for all natural numbers n, so for every tail. And what you can see beyond that is that these things are increasing, or the INs are increasing sequences. So IN is increasing and SN is decreasing. Why is that the case? Well, it comes from that nesting. You're just looking at less elements as n increases, right? You're sort of scrapping a few of the elements to go beyond into the higher values of n here. So clearly you're looking at less, so the supremum has to be potentially getting smaller, and the infimum has to be potentially getting bigger. So from before, or from our theorem in this lecture, this tells us that IN, since it's increasing, approaches its own supremum. So it's going to approach the supremum And Sn, since it's decreasing, is going to approach its own infimum. Okay, so all that is we have increasing and decreasing sequences. So now what we're going to do is we're going to define what are called the limit supremum and the limit infimum. So these are generalizations of limits of sequences. So let's take a look at a definition again. So we define this is called the limit superior. Sorry, I think I said limit supremum. So the limit superior of the sequence xn by, so this is lim sup. So we write this as lim sup for limit superior. So it's not really a limit. It's a sort of abstraction of this. And this is equal to the infimum of your SNs. So whatever your SNs are converging to, that is what you call your limit superior of your sequence. And of course, this is just the infimum of the supremum of the tails. So this is where things get a little complicated because we have this sort of inf of a sup, right? It becomes a little bit difficult to manage, but we'll do some examples. I'll show you what happens here. So, and we define the limit inferior as of xn by, so lim inf, as you can imagine here, of xn. This is equal to whatever your I sub n's are converging to. So this is your sup of in, which is equal to a sup of the infs of the tails. Okay, so that's a lot to swallow, right? That's a very difficult statement to sort of get your head around. So I propose that we do a couple of examples and we'll sort of work through this step by step, right? You sort of have to go a little bit down the rabbit hole to understand these things because you need to figure out the tail, and then you might need to find the lim, the inf and the sup of the tail, and then you need to find the inf and the sup of the inf and the sup of the tails, right? So it sort of gets very, very complicated very quickly. So we need to break this up into its constituent components. So let's take a look. There's sort of three sequences that we've been using as examples. So let's use all three of those sequences. So here's example one. Let xn equal to -1 to the n plus 1. Remember, this is your sequence -1, 1, -1, 1, -1, 1, -1, 1, -1. Okay, so then, what are the tails of this thing? Well, this is just the elements of your sequence beyond some value of n, which is clearly just going to be -1 to the k plus 1, right? So it doesn't really matter where you look in this sequence because you're just sort of alternating between -1 and 1 all the time, right? There are infinitely many ones, there are infinitely many -1s here. So then we can ask ourselves, what is the supremum of these tails? Well, again, remember the tail is just a sequence of -1 and 1. So what's the biggest value that thing can take on, right? It only takes on two numbers, 1 and -1. And so it's pretty easy to see that this thing is equal to 1 for all n. Similarly, the infimum of the tails is just the smallest value it can take on, which is -1. And again, this infimum is for all n bigger than or equal to 1. So now let's figure out what the lim sup is. Well, the lim sup of xn, this is the infimum of the SNs. But this just becomes the infimum of a constant sequence of ones, for all n. So what's the infimum of a constant sequence? Well, it's just the constant itself. So this becomes 1. Whereas the lim inf of this thing is the supremum of all of these INs, which again, it's a supremum of just a constant value. So this is the supremum of -1, which in this case is just -1, right? So these things are different than regular limits. Remember, we showed in the second lecture that this sequence is not convergent because it's not Cauchy. But the lim sup and the lim inf, they very much exist, and therefore we can see that they are different, right? The lim sup is 1, whereas the lim inf is -1. Okay, let's do another example to keep getting our head around this. Let's use this sequence of natural numbers. Xn is equal to n. So 1, 2, 3, 4, 5, and so on and so forth. In this case, the tails are just every natural number beyond some capital N. So I say beyond little n. So say little n is equal to 100, then the tail is just all of the natural numbers bigger than or equal to 100. If little n is equal to 456, then the tail is just every natural number beyond 456. Nothing special. Okay, well, if we ask for what the sup of these tails are, this thing is clearly unbounded, right? Whatever little value of little n I choose, I can go for every natural number beyond that. And so the same argument that shows that the natural numbers have an infinite supremum, again, we show that these tails as well have an infinite supremum. But they have a finite infimum. So again, this is basically the same argument that we used in the last lecture. We said that the infimum of the natural numbers is 1. In this case, the infimum of the tail is the smallest natural number, basically where we cut off, which is exactly n. Okay, so then let's compute the lim sup of xn. Well, this thing becomes the infimum of our SNs. But this is just the infimum of infinity. Again, it's a constant sequence, just like the last case. And this just becomes infinity. Similarly, if we look at the lim inf here of xn, this is the supremum of the I sub n's, which remember the I sub n's are just all of the natural numbers, so it's equal to n. So we're asking this, what is written right here is now equal to the supremum of the natural numbers, right? You're asking what is the biggest natural number? And again, we know that that thing does not exist. So this thing is equal to infinity. So what we have here is we have a monotone sequence, right? It's increasing. And we know that it's sort of converging to its supremum. So that is, it's diverging to infinity. And now we can see that the lim inf and the lim sup are both equal to infinity in this case as well. All right, let's do one more example. 1 over every natural number, 1 over n. Well, we know that this, we've already proved that this thing converges to 0 as n goes to infinity. We can say that the tails, this is just 1 over every natural number beyond little n. And so if we take a look at what our SNs are equal to, this is the supremum of the TNs. Well, in this case, the biggest number this thing can take on is 1 over n. So you're basically sort of flipping what we did in the second example. If you need to, maybe write this out. So this would be, 1 over n, 1 over n plus 1, 1 over n plus 2, 1 over n plus 3, and so on and so forth. And you can see the biggest number this takes on is 1 over n. Similarly with I sub n, you get the infimum of this. Well, it's going to take a little bit more work, but you can show that the infimum here is 0. This comes from the fact that you are converging to 0. So this thing is going to 0 as n goes to infinity. And so what you find here is that every lower bound, you can very easily prove that the infimum has to be 0, because if it's something bigger than 0, then you can always find a 1 over n with n large enough that's smaller than it, that's closer to 0. And of course, 0 is itself a lower bound here because everything in here is positive. But then this tells me that the lim sup of xn, this is just the infimum. So the infimum of 1 over n, where n is in n, right? So I skipped a step. I just said it's the infimum of Sn, but I know that this is the infimum of 1 over n. Again, this is exactly the same argument that I just made for the infimum of Tn. This thing is equal to 0. And if we look at the lim inf, this is just the supremum of a constant sequence of zeros. And so this thing is also equal to 0. Now, this is kind of interesting, right? Because we know that this sequence converges to 0. But we saw also that the lim inf and the lim sup are equal to 0. So there should be some sort of tangling between the lim sup and the lim inf. And that's what we're going to do for the final theorem of the day. This theorem says that if you have a convergent sequence, then the lim inf and the lim sup are equal to the limit of that thing. So let L be an R, and let Xn be a sequence of real numbers. Then Xn converges to L if and only if, so this is a logical equivalency. We're going to have to prove two directions for this. Well, if lim sup of Xn is equal to L, which is equal to the lim inf of Xn. Again, put this in the context of the previous example. We knew that in our case, L would be 0, 1 over n converges to 0. And so we saw that the lim inf and the lim sup are also equal to 0. What we could do now, since we calculated lim sup and lim inf, we could also say that the sequence converges to 0 by this theorem, because this theorem tells us if the lim sup and the lim inf are equal, then that's what the limit of the sequence is as well. So there is a correspondence between the limit in these things, but it's only when you have convergent sequences. All right, let me start a new page to prove this. First thing we're going to do is we're going to go in the forward direction. So that means that we are assuming, so suppose Xn converges to L. Okay, so that's what this forward implication means for an if and only if statement. We are going to show that the lim sup and the lim inf are both equal to L. So this means, so thus, if epsilon is greater than 0, there exists a natural number n such that n greater than or equal to n implies, so we're going to do this, we're going to say Xn minus L is less than epsilon over 2. So we're going to use epsilon over 2 here. It's still a positive number. This is perfectly valid. And this implies, so this implies that Sn, which is the supremum of the tail, is less than or equal to L plus epsilon over 2. And In is equal to the infimum of Tn, which is greater than or equal to L minus epsilon over 2 when n is greater than or equal to capital N. Now, I'm just going to scribble in the margins. Why is that the case? Well, Xn minus L less than epsilon over 2, you can unpack this. So you just unpack that absolute value here. This is a sort of trick that we used, I believe, in the previous lecture as well. And this gives you L minus epsilon over 2 is less than Xn, which is less than L plus epsilon over 2. And so you can see that L plus epsilon over 2 is an upper bound. That's where I see that my supremum is no bigger than L plus epsilon over 2, because in this case, the supremum is the least upper bound. Similarly, I have a lower bound of L minus epsilon over 2. And that means that my infimum is greater than or equal to L minus epsilon over 2 because it is the greatest lower bound. Okay, so that's where that piece comes from. Now, let's unpack this a little bit. So from what I said, so thus, L minus epsilon over 2 is less than or equal to IN, which by definition is less than or equal to SN, which is less than or equal to L plus epsilon over 2. So I'm just collecting the information that I know. But then, so let's unpack this. So L minus epsilon over 2 less than or equal to IN less than or equal to L plus epsilon over 2. If you just re-engineer or redo what I had in green here, this is the same as IN minus L is less than or equal to epsilon over 2, which is of course less than epsilon. And if you do the same thing, you get L minus epsilon over 2 is less than or equal to SN, which is less than or equal to L plus epsilon over 2, which the same line of argument gives you this. So I have got IN and SN within epsilon, and this works for all epsilon greater than 0. Thus, by definition, SN converges to L and IN converges to L as n goes to infinity. But since SN is a monotone sequence, it converges to its own supremum. It converges to its own infimum. And IN is a monotone sequence, it converges to its own supremum. So therefore, these things that they converge to, remember, these are the definitions of lim sup and lim inf. So this gives me exactly what I wanted. So that proves one direction, right? That's assuming that you have a convergent sequence. Then you can show that the lim inf and the lim sup are both equal to whatever you're converging to. Now let's go backwards. Let's imagine. So let's suppose that the lim sup of xn is equal to L, which is equal to the lim inf of xn for some L and R. So there's some value that this thing is equal to. So thus, first thing, there exists, I'm going to call it N1, such that if I look at n beyond little n1 or capital N1, this implies that the supremum of the tails is less than or equal to L plus epsilon over 2. So basically the same thing that I did before, same argument that I had. And there exists a capital N2 such that if I look beyond N2, I can get that the infimum is greater than or equal to L minus epsilon over 2. So the arguments for this is just coming from the fact that I am converging, right? So these lim sups and these lim imps exist and they converge to L. And so I'm just unpacking that absolute value again, right? It's the same type of idea. You're just using properties of lim sups and imps to get these things. So it's worth, pausing the video and thinking about where these come from. But these are certainly true statements. So if we, let's say, let capital N equal to the maximum of N1 and N2, right? So you told me that beyond N1 things work for the sup and beyond N2 things work for the inf. Then I said, okay, look beyond both of them together, then everything works for both the sup and the inf. And so this says, and if n is greater than or equal to capital N, so beyond the point of working for both of these things, this implies, so again, redoing the steps from above, we get xn minus L is less than or equal to epsilon over 2, which is less than epsilon. But this tells us that xn converges to L as n goes to infinity. So I kind of left out a little bit of steps here. I want you to be able to fill in the gaps, but the point is you're basically just going backwards through what I did in the previous part, right? So you're just sort of going up instead of in the last part we were going down, right? So you can rebuild everything based on what I've said here, and you're just sort of re-engineering the argument. And this sort of makes sense because this is a logically equivalent statement, right? You're saying if you converge, then your lim inf and your lim sup are the same. So it's you're sort of just moving the argument in one direction or the other if you want to prove this thing. Okay, so what we did today is we introduced properties of monotone sequences that are either increasing or decreasing. And we saw that they're going to converge to the supremum or infimum respectively. And we use these ideas to define a sort of abstract version of a limit, which is called the limit supremum. Now, through the examples that we saw that convergence sequences, and we proved this at the end, that convergence sequences, their limit is equal to the lim sup and the lim inf. But for sequences that are not convergent, think -1 to the n plus 1, well, then you can have completely different lim infs and lim sups. And importantly, from that last theorem today, we saw that when these things are different, then you cannot have a convergent sequence. We have another way of ruling out convergence or proving convergence based on this logically equivalent statement from the end today.